First of all, I'd like to acknowledge the traditional owners of the land where I sit today, the Turrbal and Yagara people, and acknowledge the traditional owners of country throughout Australia and recognise their continuing connection to land, waters and culture. We pay our respects to their elders past, present and emerging. Got a couple of quick slides, CIBSE slides for you all before we get started. At the moment, CIBSE is offering 15 months of membership for the price of 12. So if you become an affiliate or graduate member this month, your membership will be extended until the end of December next year. We've also just implemented a new system of quarterly deadlines for membership applications for chartership. So just take note of those. Applications can all be made online now. Okay, so just to let everybody know, this presentation is being recorded, so that'll be made available to everybody within the next few days. Please, if you've got any questions, put them in the Q&A box and Sven will come to them probably towards the end. Okay, without further ado, I'll hand over to you, Sven.
Thank you. Thanks, Jen. Thanks to everyone who's jumped on board. I'll bring my presentation up. You should be able to see it.
Yep.
Is that right? Yep. Okay, great. So the presentation is one that I've been running a little bit. I'd started off with as an error presentation and I've expanded it out. It basically deals with, or it looks at some of the key risks associated to commercial kitchen exhaust systems. And then at the same time, it looks at ways of minimizing these risks by engineering and with a particular focus on Australian standards AS 168.1 and .2, which are the main standards related to commercial kitchen exhaust systems. So just as a brief introduction to myself, so my name is Sven Bolomy. I'm the General Manager of AOM Australia. So we're a company that works in this space and have been doing so for quite a few years. I've put my email address up there on the first slide. I'm more than happy to take any comments, feedback, questions, as Jen said, in the Q&A after this presentation, as well as once you've slept over it, if there's a question that comes up later on when you're reflecting back on all of this. I'll try and keep the monologue relatively short. The presentation is probably around 40 minutes. I'll try and go through it as quick as possible so get more to the Q&A where we can look at specific points in more detail. So just very quickly, just a couple of slides to introduce AOM, which is air and odour management. So we work in the space of air in general, particularly in buildings. Our core business has always been related to commercial kitchen exhaust, though we have expanded out into indoor air quality products as well. Our main customers remain buildings and particularly the hospitality industry. You may have seen that in my description, I'm also General Manager of a second company called Bilby Group. So that's a spin-off of AOM where we've just taken all of our servicing that we did of servicing AOM equipment and spun it off and have now a servicing company that pretty much helps hospitality customers from anything to do to servicing their hospitality equipment with a particular focus on the exhaust systems. So tonight's presentation will focus on commercial kitchen exhaust. As I've said, I've taken out a lot of the AOM product descriptions and all that out of the presentation to really just keep it to the, let's say, the engineering side of things. But I will be showing some examples. So there are quite a few references to different products and because that's the way that we treat commercial kitchen exhaust. So one thing that I just say here, and it's hot off the press, we've just finally our new catalog. It took a while. So we have all our products now wrapped up in this nice little catalog, which is, we haven't printed it out yet, but basically the catalog goes into more detail into all these type of products and the specifications that can be applied and so on. Also, part of the catalog, a lot of what I'll say here has been summarized within this document as engineering bulletins. So it kind of gives guidelines as to how to specify equipment related again to Australian standards with the focus on commercial kitchen exhaust. So here's the first bulletin of our catalogue, is what is the composition of commercial kitchen exhaust. And that's a lot of what I'm going to say here tonight. So it pretty much summarizes. So I'm more than happy if someone wants a hard copy, once they're ready, I'll send them out, or we'll have this up on the website relatively soon. So commercial kitchen exhaust, first slide. So during the course of the presentation, I'll be looking at risks, but then I'll be looking at how to mitigate those risks through the exhaust system. And I'll always come back to this slide, just to be able to identify the different parts of the different components of the commercial kitchen exhaust system. So basically, in no particular order, we can look at, and we'll come back to these, at cooking type constraints, the type of cooking, the design of an exhaust hood, filtration systems, fan ducting design, the location of discharge points, and the balancing of the kitchen exhaust, or the kitchen space, the air balancing. So I'll be coming back to this slide and then looking at each of these with a focus on the risks. First couple of slides is commercial kitchen exhaust. So what is commercial kitchen exhaust? So we had been working in this space for quite a while. And about 5 years ago, we kind of realized, well, we're doing a lot of working with filtration systems and hood design, but we ended up figuring out that not that many people, even internationally, had really looked into what was commercial kitchen exhaust, studied what were the composition. So we set up a research project with the University of Sydney. So this was quite a few years ago now. And that research project had the objective of looking at what was actually in commercial kitchen exhaust, and then studying or analysing the different type of filtration equipment that's generally available on the market to filter out and to treat commercial kitchen exhaust and look at efficiencies and so on. So that was the objective of that research project that we ran for 6 months with the university. It also resulted in quite an in-depth bibliography study from international bibliography. So we've been able to compile all that together. And a lot of what I say today, it comes from this research project that we did. So what is it? Ultimately, what you're seeing here, this is a pretty extreme video because it's an open fire pit. You don't find those in every second restaurant. And it's grilling huge amounts of meats, Argentinian grill type restaurant. So there's a lot going on under this hood. A lot of cases, what you find is the main composition of commercial kit is just a whole load of vapor, because you're heating stuff up. It's water that's going up into the hood system. But in addition to that vapor is a whole lot of grease molecules that are attaching themselves to the vapor molecules and creating what we've called grease vapor. And the interesting, I won't say interesting about grease vapor is that it has a tendency to condensate, when there's a temperature difference, particularly in the ducting. And it's generally with this type of component that you find the buildup of grease in the ducting, because you have this grease vapor that's condensing in the ducting. The second our main component are particles. So huge amount of particles, different forms, sizes. What you see here, a lot of this particle matter, commonly referred to as smoke, because it's what you can see. So the smoke that we see here, you have, there are embers coming up, so those are large particles. Then there's a whole load of smaller particles, because there's a lot of ash also going up. But what we found is that particle matter on a standard cooking line is a whole load of grease in a lot of different forms, particularly in the very small, so the fine particle matter. And it's just grease in forming particles and then getting sucked up into the exhaust system. And once we've taken pretty much that solid component, the particles, what's left is a whole load of gases. And the main gases, which is what creates the odor component, is composed of these volatile organic compounds. So these are a whole bunch of compounds that we've been able to identify in kitchen exhaust. And then finally, a whole bunch of other gases that are really standard gases related to any type of combustion process, so CO2, CO, NO2, and so on. So when we look at treating commercial kitchen exhaust, we can work on removing grease vapor, we can work on removing particle matter, we can look at acting on or breaking down volatile organic compounds, but we can't do much about these gases here, and those are going to have to be discharged at the discharge point. So just looking a bit more in detail with regards to particle matter. So during our University of Sydney testing, we got a char grill, an open gas-fired char grill, and we flipped burgers on it. Why we chose that piece of equipment in particular, I'll come back to it later on with a few slides. It's one of the worst offenders, let's say, in regards to creation of contaminants in kitchen exhaust. So a gas char grill, you'll have the grease of burgers dripping into the open flames and really igniting and creating a whole load of particles and particle matter. So for us, it was one of the worst. It's one of the worst offenders, and we knew that prior to doing this research, and this research confirmed it. What we found in particular is that this type of appliances, like I said previously, produces a lot of small or fine particles. So it's really small stuff that's getting sucked up into the ducting, and it's not the type of stuff that gets then easily deposed into the ducting or drops into the ducting. This is the type of stuff that you see as smoke that comes out of a stack. So that's one particular first thing that we found, is there's a very high concentration of the fine particles as opposed to these larger coarse particles, which are generally stopped by a standard grease filter, a baffle or stainless or honeycomb filter within an exhaust hood. But this stuff just goes straight through. Then when we looked in the volatile organic compounds in more detail, ultimately, what we were trying to do is identify which compounds are the worst offenders when it comes to a bad kitchen exhaust smell or an odor. But what we ended up finding was just a whole load of compounds of different concentrations. We try to identify different odor descriptions to them, looking to, like I said, find the worst offenders. But there were just so many, and that's just flipping burgers over a char grill. So you can imagine that as soon as you throw in some spices or something else or some other type of cooking using woks, then you have a whole other range and composition of VOCs. Our first conclusion there was it's complicated. So with that in mind, I'll be looking in particular at 4 different impacts generally related to commercial kitchen exhaust systems. What we find often come up with in projects that we work on. The first of those is the fire risk of exhaust systems. The second is what I've called a local environmental impact. So the impact to local neighbours or who live near a discharge point, users, officers, and so on. Then there's an indoor air quality health impact related to all those contaminants in a kitchen exhaust. And then I'll briefly touch on a general urban environmental impact on a larger scale. So moving higher up from this local environmental impact. So looking at these different impacts one by one. The first one, the fire risk, so very common. And what we've found is it's common in small shops that are not necessarily abiding to standards, but it's also in heritage buildings with large, very, very respectful, let's say, kitchens. Typically, the example that I've put up here is the Brisbane Port Office Hotel, which is, again, a couple of years ago. But that fire was contained within the ducting, luckily, and didn't move out of the ducting into the whole building. And the interesting part about this example is that the fire started on a char grill. So it's not necessarily a solid fuel appliance with an open fire pit like we saw in the video previously, but here it was really just on a standard gas-fired char grill with a flame that moved up and ignited fuel ducting. The US National Fire Protection Agency have stated and do state that it is one of the leading origin of structural fires in hotels and motels is coming from the kitchens. So just to underline that it is a hot topic, pardon the pun. So key document with regards to this, and I won't be repeating everything from this document because it's quite comprehensive, is the ERA Bulletin on Fire Safety of Kitchen Exhaust Hood Systems. So that's a good piece of reading if you want to delve into that. One thing that the document does repeat as well is that it's a serious thematic, and it does give a brief overview as to why kitchen exhaust systems are such a high fire risk. And very simply put, it's this fire triangle, which is very standard fire triangle, but basically you have cooking. So you have the ignition, you have the flame that's able to ignite the fire. You have the buildup of fuel in the ducting, or in some cases within the appliances, such as gas, such as fryers, who have a kind of oil just sitting there at high temperatures. So there's fuel, there's ignition, and because it's an exhaust system or a ventilation system, you have a whole load of oxygen. So all these three elements to the fire triangle perfectly represented within a kitchen exhaust systems, and that's why there's such a high risk. So coming back to this slide and looking at the different elements as to what we can do to try to minimize this risk with these different design elements. There's three in particular that I'll look at. The first thing is identifying the cooking type and the constraints that the cooking type might result in. As a barrier between the ignition from the cooking equipment and the buildup of fuel in the ducting, you have the exhaust hood. So it's clear that the exhaust hood, which acts as that barrier here, has an important role to play, and then general ducting design as well, because that influences the capacity of the system to build up fuel. So looking at cooking type constraints, research identifies three primary types of equipment that are likely to cause restaurant fires. The first is the deep fat fryer, again, because it has that huge amount of oil just sitting there at a high temperature, and it's very much flammable cooking oil. And as I said in the first slide, it's also the appliance that generates grease vapor. And that grease vapor builds up in the ducting. So you have that source of ignition and the buildup of fuel in the ducting through this appliance. Then really anything to do with gas, because you have that open flame. So be it a char grill or even gas cooking ranges, which causes flare up. And also generally these appliances are used with very fatty type foods, examples of steaks and burgers. And fatty type foods means more buildup of fuel in the ducting. And then you have, of course, and this is a lot of cases that come up with restaurant fires that come from solid fuel. And the more there's solid fuel in restaurants, the more the risk of this fire comes up. So AS 1668.2 has a clear statement with regards to solid fuel. and the constraints around solid fuel. And that statement is that any charcoal and solid fuel appliances should or needs to have a completely separate exhaust system. So there's no mixing of solid fuel and non-solid fuel appliances within the one exhaust system as per that standard. And the reason is, so one, solid fuel, of course, you have a higher risk of ignition, and the non-solid fuel appliances, which are generally deep fat fryers and the likes, will build up fuel. Solid fuel generally runs at such a high temperature that it burns off a lot of fuel, whilst the non-solid fuel appliances build up the fuel in the ducting. So when you blend the two together, you get a higher risk of fire. So that's why Australian standards, that section there, pretty much say 2 separate systems. So one thing that I have come upon recently when dealing with this is the scope of this standard. So it's one of the first statements right at the beginning of the standard says, this standard is applied to new designs and new builds. So you have a lot of situations where, of course, it's retrofitting new restaurants into old design and old builds, where it's impossible to have 2 different exhaust systems because it hasn't been designed that way. So that's when this clause can be bypassed and systems to minimize the risk of fire. So as I said previously, exhaust hood design, so it comes down to AS 1668.1 2015, where we're looking at the exhaust hood as the barrier between a potential ignition and the build-up of fuel in the hood. And Australian AS 1668.1 states, and the key statement is here with regards to flame and spark arrestance. So basically, when you have an exhaust duct in a building with more than 10 meters of length and an exposed flame or embers, so embers is clearly when you're using solid fuel, exposed flame would refer to gas type appliances as well as solid fuel. Here the statement says that unique device flames in accordance with UL 1046 incorporated into the exhaust hood or filtration systems. So UL 1046, looking through it, there's a couple of elements with UL 1046. One, it wants, or any grease filter within the exhaust hood needs to act as a flame barrier. So it means effectively stopping a flame from moving up through the hood into the plenum, into the ducting. So testing has shown that baffle filters in that regards respect that flame barrier. Honeycomb filters, I have not seen a honeycomb filter that has successfully passed that test. So that means that baffle filters are the way to go when these requirements are met in a project. And then it goes on to say that any parts of grease filters that are exposed to cooking effluent shall be constructed of non-combustible materials. So you also need to have that proof that any type of grease filter, so here it goes back to infiltrations as well, should be built of non-combustible material. So basically it means that even a filtration system located in a ducting should be built of non-combustible material. So looking at the exhaust hood, not only as just a barrier between flames moving up through the ducting, but also the first or the best means of filtering out grease particles prior to grease particles moving into the ducting and accumulating. So this is when we did our research with the University of Sydney and tested different forms of filters or filtration equipment that we could effectively position into an exhaust hood. So what we have here is HCF is honeycomb filter, so just a standard or grease filter located in the exhaust hood, grease filter with UV built into the hood, a grease filter with electrostatic precipitators located into the hood, double pass electrostatic, so that's 2 electrostatic precipitators, one after each other, also located in C, which is activated carbon. So we tested the different efficiencies of these filtration methods, and to no surprise to ourselves, because we'd been using this method the most over previously, was the double pass electrostatic precipitator that was able to achieve the highest efficiencies of particle filtration. So removing grease particles within an exhaust hood, and we were looking at efficiencies into the high 90% of filtration. Again, this is with flipping burgers over a char grill, producing a lot of contaminants. In these situations, a UV treatment really didn't have a significant effect on the amount of particles that were getting through the exhaust hood. Moving on to ducting design, this refers back to AS 1668 and how to minimize or how to design ducts or a whole project so that you minimize the risk of buildup of grease. So horizontal, the key statements are horizontal ducts to a minimum, access requirements, of course, for maintenance. That's really just summarizing very briefly that standard. Another interesting piece of bibliography, it's an older type document now, it dates back from 2002, but it does look into the different ways that particles or grease builds up in ducting. And it looks at these three different grease deposition methods in ducting. So you have gravitational, with particles dropping down due to gravity and building up in the bottom of the duct. You have turbulent deposition, which is caused by turbulence with the air in the ducting and particles being smashed on the sides of the ducts in particular, and then building up within the ducting. And then there's that temperature differential that I discussed previously, where you have the condensation of grease vapor in particular. And so this document looked at these three different methods and looked at, in particular, velocity through ducting. So in Australia, we generally design horizontal ducts to a velocity of, I think it's about 10 meters per second, a little bit under perhaps. So this document looked at, well, what happens if we start varying the velocity and bringing that velocity down? Does that significantly increase the amount of particles or grease that's building up in the ducting? And basically, the answer, very summary to that, is no. The results were that in the majority of cases, you could bring the velocity down to 2.5 meters per second roughly, and still have the same type of buildup as you would have at 10 meters per second. The reason being that when the air goes fast, you have less gravitational settling but more turbulence. When it goes slow, you have more turbulence, and no, the other way around. When it's slower, you have you have more gravity, less turbulence. Fast, you have a lot of turbulence, and those kind of balance out. That's the majority of cases, because then condensation, if the air is slow and you have big temperature differentials, with ducts going outside in Canada or wherever, then you do have a lot more condensation issues. But in majority of cases, velocity was not necessarily a reason for increased grease buildup in ducting. And one of the main conclusions is with this document is, well, that opens up the possibility for demand control ventilation, where we can still design a ducting to run at 10 meters per second, say for 2,000 liters per second. But we can safely say that we can bring the air down to 1,000 liters per second if the kitchen's not being used at full speed or as intensely as at 2,000 liters per second. And we can safely bring that down, bring the fan speed down, improve the energy consumption of the system, whilst not necessarily creating more of buildup of fuel. So key responsibilities to minimize this risk, and this is a type of slide. This is a slide that I'll come back to each of the risks. Of course, a system that's well designed to applicable Australian standards and best practice, that's important. that the overall system be supplied and installed as per that design. But ultimately it is, and it often comes down, and we see this with fires in buildings, it comes down to the end user and the capacity that the end user has to maintain the exhaust system, and has the will to maintain the exhaust system as well. And that's one thing that, because I'm in a working group with within ERA, ERA have set up a working group that has a particular focus of fire risks of exhaust systems and how to ensure through maintenance of the systems and proper design to allow for proper maintenance of the systems, that we're able to minimize that fire risk. And this technical group is looking to establish a best practice guide to be able to underline industry best practice as to how to maintain this system to decrease the risk. But the key element there is that it's really the capacity to maintain these systems that's important. So moving on for example, just a quick example here, W Hotel up in Brisbane. It was part of a new development at 300 George Street. For the hotel was, and for the overall mechanical design of the exhaust systems, was to minimize the buildup of fuel in the ducting. So some of the restaurants were at lower levels, some were at higher levels, and they just wanted to capture the grease, as much of the grease as close as possible from the source, which is the kitchen equipment. So it's in this case that the exhaust hoods that we supplied were the ones which I detailed previously, with inbuilt electrostatic precipitators to be able to remove up to 90 to 95% of the grease within the exhaust hood. And with proper maintenance of those systems, we're continuously removing the grease out of the exhaust hoods, and that's stopping the buildup of grease in the ducting. So there's also a requirement for servicing, of course, of these exhaust hoods. Now moving on from and into the local environmental impact. So here, this is a CFD analysis done by ERA in Melbourne, in a laneway in Melbourne, which is located very close to their office. And they were smelling a lot of kitchen exhaust within their offices, and they wanted to try and understand why. So they sent an intern out to do a CFD analysis of the discharge point. And they realized that this discharge point, which was totally non-compliant to Australian standards and discharging untreated exhaust in this laneway, was causing this air to build up in the laneway, move up and up through here, where there was all the open windows and the ERA offices, and also out towards the front. So this discharge point was really an example of a very high environmental or high local impact discharge point. So AS 1668.2 pretty much defines the requirement for the discharge of commercial kitchen exhaust. So it runs throughout the standards. So I've just taken out some of the key elements here that we'll discuss in a bit more detail. The first one is the chapter related to air discharges, and the statement that says that any discharge needs to be, exhaust air should be discharged to the atmosphere in a manner as to not to cause danger or nuisance to occupants of the buildings, neighbouring buildings, member of the public. So one of the key words here is the word nuisance, and it comes out quite often within the standards. So nuisance is the key word. And then a bit further on, and this is a particular chapter related to concessions, so whether or not you can discharge horizontally or not. One of the key words here, and it also comes out quite often within these standards, is the notion of odour. And odour is pretty much the parameter that we find also that exhaust systems are judged upon, is the capacity of whether or not they're producing odour. So what is the nuisance? A general definition: environmental nuisance defined as an unreasonable interference with an environmental value caused by emissions of aerosol, fumes, light, noise, odor, particles, or smoke. So in kitchen exhaust systems, we have a lot of these. I won't talk about noise of the fan. That happens occasionally. Light, probably not, but aerosols, fumes, odor, particles, dust, smoke, it's all there. With a particular focus, like I said, kitchen exhaust systems focus on, or Australian standards look in detail with regards to odor. And one of the reasons, in my opinion, that is because if you can prove that you can remove the odor of your exhaust system, you're pretty much proving that you remove all the other elements as well. So aerosols, fumes, particles, smoke, simply because you won't be able to act upon the odor component if you've not taken out that particle or that visible component. So by taking out the odor, you prove that you're dealing with all the rest. And I think Australian standards also focus on odor because it's one of the main causes for complaints related to restaurants. People will generally say, well, I'm smelling this smell all the time. And that's something that comes out with this document here. So food and beverage tenancies and their impacts are regulated by local councils. And local councils have this document here, which is Air Quality Guidance Note, that they use to evaluate whether or not there's a particular impact from or a restaurant is causing a nuisance. Without going into detail, because it's quite a meaty document, in 3 statements, complaints from food outlets usually arise because of frequency and duration rather than intensity. So that means that if you're walking down the street and you get an intense smell of bacon, you're probably not going to run to your local council and complain. You're probably going to go buy a bacon and egg roll or similar, whatever your liking is. If you have an open window and you live above a restaurant that every day between 10 and 12 o'clock, you're smelling bacon, so you have frequency and duration there, you'll probably go and complain to council because you can't stand the smell of bacon anymore. So then what local councils can do is, and we have seen it, is they can impose compliant testing. And compliant testing, from what we've seen, is generally always focused on odor. They're not going to go look at whether or not there's smoke. They're going to look at whether or not there's odor emissions at a discharge point. And ultimately, local councils have the power to issue prevention notices should they deem that a restaurant is causing an offence. And we have seen it escalate to shops closing down because they could not abide by the council notices. How is odor emission? How are odor emissions judged? This is New South Wales. I'm assuming that every state has pretty much the same regulations with regards to odor emissions. So this is an even meatier document, which I won't be looking into too much detail, but it does underline the steps to implementing a compliance review related to odor emissions, stationary source, or a discharge point from a restaurant. One of the key matrices with regards to restaurants is this one. And one of the key statements that I've taken out of it is this one. So, is the facility doing everything practical to minimize the impact and not expand or change its method of operation? So the idea of everything practical to minimize the impact. So that's an important statement because it pretty much says, well, is the restaurant running a fully compliant with the filtration system, that's properly maintained? And if it is, then it's pretty much putting that restaurant or that building on the right side of compliance. And restaurants, when councils may tend then to say, well, yes, the restaurant's doing everything possible and it has been designed that way and it's operating that way. So really, should a complaint arise, a council might favour the restaurant in that case. And I'll come back to one of the main reasons for that. And I'll look at this example, which is an example of council really looking into, with a fine comb, one particular tenancy. So this is the Bondi Pacific development, Bondi Beach in Sydney. It used to be a hotel, and the new building, the people who bought the building, developers decided that they'd redevelop to luxury apartments and food and beverage, or tenancies down below, which ultimately were a whole load of food and beverage tenancies. But because it was, the original design was a hotel development, they didn't have a whole bunch of, they didn't have room, and they didn't have the ventilation system or exhaust system to transform each of these spaces into a common exhaust system going up onto the roof. So basically, each of the tenancies on the ground and second and first floor needed to be evaluated independently and discharged independently at different points through the building. And ultimately, these are horizontal discharges, and they need to be designed so that they comply to standards. And one of the toughest ones was the Bondi Pacific, the club, Pacific Club, which had a fully solid fuel open fire cooking line. And council, in this case, the local council, as part of the DA application, said, well, prior to giving final approval for the shop to open, we want an independent odour assessment report carried out with conclusions from an independent expert. So this was done once the whole restaurant had been fitted out. We supplied all the filtration equipment to be able to achieve compliance. So right the day before opening, the independent odour consultant came down and did the test for compliance. So what it came up with, one, it was a pretty stressful time for us, but what it came up with was odour emissions of 5,000 odour units with no filtration, and roughly 600 odour units with filtration. And the Australian standards to determine that is Australian Standard to Odour Assessments, Determination of Odour Concentration by Dynamic Olfactometry. So it's a sensorial test, which is a sniff test with a panel of experts that receive a sample of contaminated or sample of air, and that judge the odour composition or the odour concentration within that air. So of course, a non-filtered sample smelled of smoky cooked meat, which is logical because it was an open fire pit cooking meat, while a treated sample smelt of musty ozone smell. So it had been treated, but using ozone, so that type of smell came out afterwards. But the conclusion here is, because it's a sensorial test, and because odor is such a sensorial element attribute, you'll never get zero odor in a discharge. You will always find something, even if the discharge smells clean. There's always going to be some form of odor concentration in that discharge. So having said that, here are the elements that we tend to work with when we're looking at this local environmental impact. Cooking type constraints, of course, the type of cooking is going to heavily influence what you can and can't do, or the potential impact that a restaurant will have. Solid fuel as opposed to a small sandwich press. Then the design of filtration systems, because this is the main tool to be able to mitigate any type of cooking emissions. And then the location, of course, of the discharge point. So cooking type constraints. Well, I've already said before that there's a big variance between different type of cooking. In particular, the use of the char grill, which was the red flag for us when we've got a char grill or solid fuel within our cooking equipment. But it comes down to also the type of equipment, the cooking method, temperatures, type of food, fat content of the food. So there's a lot of different parameters that might influence the amount of particles and the amount of emissions from a cooking line. But again, solid fuel and char grills, huge contributors to emissions And a burger that is over a char grill with an open gas-fired flame, with an open gas flame, will produce 10 times, easily 10 times more emissions than if you put that same burger over just a griddle. So it's really, it makes for a whole lot better burger, in my opinion, but it just makes for that much more emissions. So when we're designing filtration systems, we need to be looking, or it often helps to be able to look at the type of cooking that's going to be associated to that filtration system. And ultimately, a well-designed filtration system, we can decrease frequency, the duration, and the intensity of emissions, and be able to remove that risk of causing that nuisance, as discussed previously. So filtration systems will, the objective, as I said previously, was first remove the particles. So once we've been able to remove the particles, we've removed that visible smoke, but then that lets us hit the second stage, which is act on the odor. But first remove the particles. So here's our burger that we put over the char grill. It's sizzling on the char grill, and then we flipped it, and it's made this huge peak of concentration, because once we flipped it, all the grease that was building up on the burger has fallen into the gas flames and caused a huge plume of smoke that's gone up into the exhaust hood. So it's become a whole lot more intense. So there's a lot of peak and troughs. Nothing's linear with kitchen exhaust systems. But what we were able to do with the filtration system is pretty much remove that intensity of the exhaust system. That large plume of smoke, we've been able to, you know, iron it out and remove all those particles. And then once we've removed the particles, then we can act on the odor. So second is mitigate the odor. There are two key tools that we have that are generally used in industry to be able to remove odor from kitchen exhaust systems. One is the use of ozone, and two is the use of activated carbon. From what we found with the research at Sydney Uni, looking at the chemical composition of exhaust systems, both ozone and activated carbon were able to remove roughly 90% of all VOCs in that burger flipping exercise. So we have we're able to achieve high removal efficiencies. And that corresponds well with what we were able to achieve in situ. So the example that I showed previously at the Pacific Club, where we were able to remove roughly 80% of that smoky cooked food smell. So these are the type of efficiencies that we're able to achieve with odor, is roughly 80 to 90%. And what I didn't say previously with the example at the Pacific Club was because there are no clear values in Australian standards, you must achieve this and then you pass the test for odor emissions. It comes down to the independent consultant who says, yes, this is in line with best practice and we recommend opening the shop. And that's ultimately what happened at the Pacific Club. So it was a good news story in the end, is that the independent consultant said, yes, that's in line. And looking at where the discharge point is located, we recommend this shop to be open. So it comes down to that. Then ultimately, it also comes down to where the discharge point is located, because depending on where it is, that will heavily influence the potential for impacts with regards to this. So both AS 168.1 and .2 have something to say about discharge points. AS 168.1 tells us that ducts route is possible to the outside. Sometimes this statement contradicts itself, but that's what it is. And AS 168.2 defines the requirements for the discharge of commercial kitchen exhaust systems, depending on the airflow. So if the airflow is under 1,000 litres per second, the emission or the discharge is not deemed objectionable, and ultimately there's no constraints other than made a nuisance. So you can discharge air under 1,000 litres per second wherever you possibly can, but you can't create a nuisance, and you still have to respect minimum separation distances from intakes, boundaries, and so on. And then when you have airflows of over 1,000 litres per second, these are deemed objectionable, and there are more constraints to discharge it. These discharge, they should be vertical, 5 metres per second discharge vertically, though Australian standards do allow for concessions for over 1,000 litres per second, where you have to prove that you are able to remove the odour through independent testing, and that these systems will be maintained. So just look at each discharge point very quickly individually. The ones that we come up on often find total discharge at the top of the building, fully compliant. There's a limited risk of nuisance, but it's not always a feasible option, particularly with very high rise buildings. So often what we find is this podium level discharge, which is respects AS 168.1 as well, in that the duct lengths are lower, so you stop at a podium level. It's also compliant because it discharges vertically. Though depending on how the podium is used and the surrounding area of the podium, there is a risk of nuisance. So we've been exposed to some projects with a vertical discharge at a podium level, but because of apartments and open spaces, there has been the requirement for filtration there. Then we often find, and the W Hotel in Brisbane was one of these cases, a high level horizontal discharge. So we find that these discharges have a limited risk of nuisance because they're located higher up from a street level discharge, but they are non-compliant. And in respects to that, Australian standards, you need to tick the boxes and say, well, I've got filtration equipment to be able to discharge horizontally. And then finally, there's the low level horizontal discharge, which is non-compliant. Of course, because you're at a street level or at a lower level, there's a high risk of nuisance. Though because there's less ducting, there's less overall design through the buildings, they're quite easy to implement, particularly if it's just a small sandwich press that you have to exhaust, or small fryer and so on. Very easy just to have a horizontal discharge and be able to prove that you filter out and remove odor. Of course, when you're dealing with char grills, solid fuel, it becomes a lot more difficult to implement. So just two discharge point locations, both low level horizontal, one that works beautifully, CBD Perth, surrounded by parklands, this burger restaurant which discharged horizontally. But because of the way where the building is, with full filtration equipment, this works perfectly. Never had an issue because the remaining air that comes out, the heat, the 10% of odor that still remains, CO2 as CO and so on, or the other gases are dispersed within this space. So that works perfectly. Here, a discharge at the entry of a car park in CBD Sydney. This one would cause us a lot of headaches because the air that was coming out here would just go straight into the car park, where a couple of security guys were working and who was still smelling the remaining 10% of odor which was being accumulated in the car park. And they ultimately complained to the building, who came to us and said, well, what's going on? You've got filtration equipment in here, should be working. So this is a case that even with a lot of high level filtration, still run into problems. So key responsibility to minimizing risk, design. And the key is here, as I said previously, if a restaurant can prove that it has been designed and is operating so that it aims to minimize risk, then councils, if there is potential nuisance, will act in favor of the restaurant. So you might have a restaurant discharging kitchen exhaust, 10 open windows. Because it's a sensorial element to odor, you might have one person complaining, that person complains to council, council looks at what's going on in the restaurant, it's perfectly compliant with filtration equipment and whatnot, and that's been maintained. Council would generally say in that case, look, one person, I'm sorry, that you can continue operating simply because you've met all the requirements. So it really comes down to design. And it's just so much more difficult to retrofit filtration equipment once a person has complained and the council has decided, yes, that complaint is legitimate. It is very difficult to retrofit the equipment to meet then the council requirements. Back to the Pacific Club, just to show you what type of in to achieve what we were able to achieve. So what we've called a triple pass electrostatic filter. So not just one filter, but three going one after each other. So these are electrostatic 1, 2, 3, just because of the high level of concentration of particles. So when filter 1 starts, it can achieve 95%, but then it starts getting dirty. So filter 2 takes over, and ultimately filter 3 also acts as a backup and does a bit of the work until servicing is done. There's also a misting system in here just to stop any potential sparks or embers to get through. Some ozone to remove the odor, and this is serviced quite regularly as well. Another example is the QV building in Melbourne, where here we had to, and this is a perfect example where the building was built, but without filtration systems, but with sensitive discharges around loading docks, car parks, and so on. So we had to retrofit filtration systems into the building for each individual tenancy. And these were supplied as plant room filtration systems. And ultimately, because there were so many issues, these were very much over-engineered, just because the building wanted to make sure that there were absolutely no issues moving forwards. So we fitted these in these are called ecos, so they're all in one, but these were supplied individually because they had to be built within plant rooms with limited access because the building was already built, and we had to fit all these units through doors. So these come with exhaust fans and so on. Moving on, indoor air quality, health impact. I think I'm taking more time than I promised I would. Sorry, but I'll try and get through the rest quite quickly. Contaminants, all the contaminants that we saw at the beginning, they form the basis of any indoor air quality. So you have particle matter, carbon monoxide, volatile organic compounds, and so on. So basically, if you don't exhaust the air correctly, you're creating an indoor air quality issue. Key elements to work on here is the exhaust hood. You've got to get it right and tied to the fan. So how much air are you sucking out of this space? And then it comes down to whether or not the space is correctly balanced. So balancing the kitchen exhaust space, this is a good document regarding designing high-performance commercial kitchen ventilation systems, as the name says. So this document looks at how to balance space and how to minimize energy consumption while taking into account balancing the overall kitchen space. So one of the key recommendations of this document is minimize the exhaust requirements. So less air you have to take out, less air you have to put back in, and ultimately, how do you do that? And then with regards to balancing the space, this is very much a standard practice now. So 80% of the exhaust air is to be replaced in the kitchen space. So generally what we recommend is that that's done in or close to the exhaust hood at 60%. Remaining might be air conditioning of the space at 20%, and then a balance of 20% as transfer air. So movement of air from outside the kitchen into it. And any type of, particularly close to the exhaust hood, any type of makeup air solutions need to be displacement ventilation systems at low velocity as opposed to mixing ventilation. So how to minimize exhaust rates? Australian standards AS 168.2 give us this option, which is section 3.6, and it's the use of proprietary exhaust hoods as opposed to just standard exhaust hoods. Proprietary exhaust hoods need to be designed to a proven and tested standard. So you should get a certificate that says, here's the standards it's been designed to. And ultimately, their airflows are generally, in most cases, lower than a standard calculation because they refer to other international standards, and the particular focus is German guideline VEI 2052, which has, in the meantime, now become the European standard and is applied throughout Europe. And that's a standard that looks at each individual cooking appliance and applies an airflow to that appliance based on two things. The first one is the amount of heat that is produced by that appliance, so the amount of heat that you need to suck out, and two, the amount of condensation that appliance creates as well. And then based on those two calculations, you take the bigger of the two, and that becomes your airflow allocated to the exhaust hood. And one of the main reasons why this produces less exhaust air than a standard calculation, because you're looking at each appliances individually, as soon as you have an empty bench space, which is quite often the case in exhaust systems, that's 0 liters per second of air. Then you might have a fryer and a char grill, and you allocate air to that. Also, when we're doing standard calculation, you take the worst case offender, which might be the char grill, which has a very high exhaust requirement on a standard calculation, but you apply it to the whole hood. So even if you have a fryer or some lesser appliances, you apply that char grill to the whole hood. So that produces a high airflow. So the advantage to these proprietary type hoods, which are the main brands that you find on the market, so they minimize the airflow. There's integrated makeup air systems. You get inbuilt filtration systems such as UV or the electrostatic precipitators, and there's more flexibility in the design, particularly in smaller spaces. So looking at the responsibilities to minimizing risks, in this case to supply, install, and particularly the capacity to ensure a balanced work environment. So you can have, in theory, all the airflows lining up and so on. It comes down to whether or not that has been balanced correctly, and that's done at the commissioning of the system, and that's the key requirement there. Finally, and just a couple of slides on this urban environmental impact, very brief. It's just to say that general research shows that kitchen exhaust systems do produce high particle matter concentrations that are significant within a general urban air quality review. So 2 studies that were done in the States, these are the key statements from these research projects, just to underline that they do have an impact. And more recently, I just saw this the other day, there's a Guardian 2019 article, which also summarizes a lot of research that's been done internationally. Here's one of the statements out of Pittsburgh, that they had a car driving around and found that particle pollution downwind of restaurants was greater than from major roads. So there's a lot more particles coming out of a concentration of restaurants than there is on a major road. So there's really nothing much from an engineering that can be done, particularly with this more general urban indoor urban air quality. It's going to be difficult to tell a restaurateur you need to put $50,000 worth of filtration equipment so that you minimize your footprint on the urban air, particularly with how standards are today. So it really comes down to whether or not a project developer is willing to invest that type of money. What we find is, and I'll just run through these 3 different scenarios with their project development. The first is a do nothing approach, where there's no reason to go fit in expensive filtration that then has to be maintained. But what we do find as a general overall approach, and moving into a second type of scenario, which is more a voluntary treatment. And that voluntary treatment, it often relates down to filtering particle matter. So getting rid of a visible smoke or filtering grease as close as possible to the hood to stop grease buildup in ducting. So that's something that we find more and more often. So a case is that fire the video of the fire pit. So that's in a hotel, and the hotel didn't want their guests to be looking at a blood stack of or plume of black smoke coming up from a podium level where all the hotel rooms were overlooking. So they decided to put some form of particle filtration to get rid of that visible impact. Another example here is a restaurant in a heritage building with the insurance company telling them you need to minimize buildup of grease and the fire risk of your system because otherwise we won't be able to insure your exhaust system or your restaurant in this heritage building. And the third scenario, one that we've discussed through this presentation, is this compulsory treatment. So because you have to apply Australian standards to discharge, to air discharges, you need to filter out the particles and then mitigate the odour. And in those cases, those are the cases where you need to prove that you're achieving that and ultimately come up with a performance certificate from the solution that you have proposed that pretty much details all the independent testing and so on that comes with the equipment that you have proposed. So that's where I'll stop with the monologue. So thanks a lot for listening. I'll probably move to questions and start with the ones that are already up on the Q&A section. So I'll start with Andreas, who's said Australian Standard 1668.1 requires 300 separation or fire installation between ducts and combustible material and separate shaft for kitchen exhaust ducts. Yes, totally correct. And that's not something that I went into too much detail, but it is clear that one of the means of minimizing fire risks is also respecting those clauses in AS 1668.1 is separation distances from ducts and the reason there is because the temperature that you can get in an exhaust duct becomes so high that if you have a piece of wood or something that's located close to that ducting, it can ignite. And that's why you need those separation distance or fire installations when you're moving into different fire compartments. Thoughts, Andreas goes on to say, thoughts on combustible materials, i.e. does this include the ceiling itself, other ductwork, stainless steel or flexible? Good question, but from my reading of the standards, it's really anything that has the objective of filtering out grease. So that's the grease filter located in the hood clearly should not be made of a combustible material because it's also the first barrier between any flame moving up through the ducting. But then any type of filtration system that has the objective of filtering out grease. So we generally stay away, particularly when the standards that more than 10 meters of ducting and an open flame. We stay away from anything to do with mechanical filters, so bag filters, HEPA filters, and so on, simply because one, they're not made of non-combustible material, and they have a tendency of accumulating grease within the filter, and it, as opposed to an electrostatic precipitator, which precipitates grease out of the ducting, these accumulate grease. So they're both made of combustible materials and they accumulate grease. So ultimately they significantly increase the fire risk of a system. That's a thanks. Thank you, Dave. Thank you, Dinesh. When duct needs to run over 10 meters within a building, which pre-filters do you have available? So yeah, coming back to AS 1668.1, it comes down to, so you have those two requirements, one, over 10 meters of ducting, and two, an open flame, so a gas appliance, or embers, a solid fuel appliance. Generally, you need to meet, so that's when you have to meet UL 1046 standards. And like I said in the presentation, we've tested our honeycomb, stainless steel honeycomb filters. They don't meet UL 1046, but stainless steel baffle filters do. And the UL 1046 test is quite stringent. It is a high level test to check to see if a grease filter acts as a flame barrier, so that the flame goes through. And I think it's, off the top of my head, it's got to, for a couple of minutes, that flame should not be visible at a distance of 3 feet from the other side of the filter. And if that flame is visible, then your filter fails. And the only filter that's passed that test are baffle filters. So really, baffle filters are recommended in those scenarios. Any risk with discharging ozone? Good question. Yes, and the answer is yes. So Australian standards to be compliant for a horizontal discharge or for concessions to dance points. There's one, you have to prove you're able to remove the odor. 2, you have to minimize the risk of emitting any other contaminants, so such as ozone. And 3, you have to prove that you're going to maintain the system. So ozone is a reactant gas. And if the concentrations are too high at a discharge point, and depending on where the discharge point is located, it's not going to kill anyone, but it does cause a health issue, because it does in your nose and it becomes itchy and it's uncomfortable, and it's not something that you want happening at a discharge point. So open window, discharge point, ozone accumulating into an apartment, that's not what we want. So in those cases where there's a risk where ozone becomes the nuisance, then we work with activated carbon. So we'd rather say, look, we're not going to use ozone, we put in activated carbon. There are other cases where you can minimize the amount of ozone that you produce or that you put into the system. There are different sensors. You can have ozone sensors at a discharge point. You can limit the amount of ozone that you put in by tying it to the intensity of the cooking. So there are different tools that we can use to try and minimize the discharging of ozone. But that's one of the key reasons that we would not use ozone, is that there's a risk at the discharge point as well. So that's got to be carefully engineered as well.
Any other reasons why you would or wouldn't choose ozone over activated carbon?
So activated, like I said, there's advantages and disadvantages to both. So ozone works very well, it's proven, and it's relatively cheap to maintain, because there are different type of ozones. So the UV systems are also ozone producing. So as soon as you have UV in an exhaust hood, that's also producing ozone. A UV tube will produce approximately, just to give an idea of quantities, 10 grams of ozone an hour on average. Then you have ozone generators, which are boxes that produce ozone and then pump ozone into the ducting. These are located outside of the ducting, so they're quite easy to, you connect it to the duct. Occasionally you check to see if it's working properly, but they're very low maintenance, and they don't have any resistance associated to them. So they're very easy to use, and they produce up between 30 to 50 grams of ozone an hour. And that's in line with what we've found with, particularly with heavy type cooking, the requirement is what you need to be able to have a significant impact on odor. 10 grams an hour is fine for very light cooking, but as soon as you have heavy cooking, you need a lot more ozone. And but then you just have to make sure that you have time within the ducting for the ozone to work. So if you have 2 meters of duct to your discharge point, forget about it. That's not going to work. You're just going to be blowing out, 1, a whole load of ozone, and 2, a whole load of odors, because the ozone won't have had time to mix together with the odor and work its magic. So you need sufficient ducting. So our minimum requirement is that the contact time is 2 seconds. So if you have 20 meters of ducting at 10 meters per second velocity, then that's the minimum requirement, is those 2 seconds. Otherwise, we switch to activated carbon, which is also works just as well. The main inconvenience with activated carbon is 1, high system resistance, and 2, a requirement of servicing. So that, and it's relatively more expensive to service activated carbon than it is ozone. But then you don't have those risks of ozone discharge, because the carbon doesn't have any of those risks. What we have had in some situations is using both at the same time. We're really very sensitive discharge points. We'll put ozone in at the kitchen as close as possible to the hood. We might have quite a bit of ducting, but we finish off with a final treatment of activated carbon, and that works really well. The only inconvenience is that there's you're paying for twice the equipment than one or the other.
How often do they usually have to be replaced, the activated carbon?
What we find is when we maintain systems, rule of thumb is heavy type cooking, 3 to 4 months. So that's char grills or solid fuel. Medium type cooking, so maybe some griddles, doing a few burgers, might be 6 to 8 months. And light cooking in a cafe, that's more like every year.
If you've got ozone further upstream, does that reduce it again?
Yes, yeah. So what happens is the ozone's breaking down a lot of the odor upstream. The carbon's being used to capture residual ozone and capture any potential remaining odors, but it's working a lot less with the ozone in the system as opposed to the carbon on itself. So in those cases, you can often double the time for replacement.
Okay, cool. I've got one more question from Peter, just on fire rating. As you know, 1668.1 requires ductwork to be fire rated when it passes through an adjoining fire compartment. Peter's just wondering why so many contractors fail to install fire rating through the car park, particularly in their shopping centres. Yeah. Any thoughts on that at all?
I'm not a fire rating specialist, so I can't, but it did come up the other day with a contractor, and I think it's they don't understand why. And this was a contractor but it's a car park. Come on, it's just the notion of why it was done was just not there. They kind of understand when fire compartments are within a building, because all of a sudden you have the fire risk is, there are people there and so on. But in the car park, from what I understood, that they had just not thought that it was something that should be done. Other than that, like I said, I'm not a fire engineer, so my knowledge on that is limited.
Yeah, it sounds like a good explanation.
Hang on, I've got Vlad. I missed Vlad's question. Are the differences in required carbon media composition for different cooking equipment types? We run with, so we have a carbon supplier which is based in Melbourne and Brisbane, and they have a specific carbon which is focused on commercial kitchen and treatment of that level of odor composition. So they supply that with the spec sheet. I know there are other forms of carbon, and I have seen other things with mixes of carbon and some others, but I haven't gone down that path. So I ultimately we use the same composition for all our exhaust systems when we use activated carbon. Does the catalogue look at different types of cooking and best treatments? Asian, we have more vapor compared to burger. Yes, there is a table in our catalogue that pretty much looks at, tries to understand what the different type of composition of cooking and apply different filtration equipment to those different type of scenarios. That said, particularly when you need to, like I said, when you need to have a performance certificate, that's you can clearly say we are able to achieve 90% of odor. There's not that many different type of options there. It really comes down to electrostatics to remove the particles, be it with an Asian type cooking or a burger type cooking, and then the odor mitigation equipment, so ozone or activated carbon. The only difference is, so Asian type cooking with woks will produce less of those very fine grease particles, more of the condensate. So it's a bit more easier to treat than it is the burgers. So in certain situations, we don't need as much filtration as compared to a burger place. So we're able to, I was talking previously in passes, so a number of passes of electrostatics, first, second, third passes. Like that solid fuel system at the Bondi Pacific, that was a triple pass, so 3 filters, one after each other. We wouldn't apply that for Asian type cooking. For some burger places, we would, just because the amount of particles are a lot higher, and they're also very fine particles, very difficult to capture.
Okay, I think that's all the questions. All finished. All right. Thank you so much, Sven.
All right. I'll put that slide on now.
So you've hopefully been able to grab Sven's email if you wanted to get in touch with him. If you want to give me any questions for CIBSE, it's secretary@cibse.org.au. We've got another seminar coming up next week on safely reoccupying buildings after COVID. And just to confirm, this has all been recorded, so we'll put it up online within the next few days. Okay, I think that's it. Thanks very much, Sven.
Thanks again, Jen, for organising and for inviting me.
Okay, see you all next time. Goodbye.
Bye, good evening.